Hey there. In this recording, I'm going to describe how you can interpret the Lorentz Fitzgerald transformation in terms of well known properties of mass or of atoms, namely the, uh, the property of time, which we all know and love, and distance, unit distance, and the property of mass. So, in a previous recording, I described how we can derive the Lorentz Fitzgerald transformation using spheres. I explained that it's essentially a Pythagorean theorem where you apply spheres to the vertices, and the vertices represent the diameters of those spheres, and the essentially the Pythagorean theorem adds up the areas of those spheres in terms of the the vertices opposing the hypotenuse, and then you get a resulting sphere, which is the sphere that is moving, and that's what I call the B sphere or the moving sphere. So, um, as we all know, if in special relativity, Einstein then went on to apply the properties of that transformation to time and to unit length and also to mass. So I'm going to just cover those three items in this recording. Um, so the first one is maybe from a kind of a personal viewpoint, a very interesting one, a time one. We look at a clock, we see it ticking at a certain rate, and therefore we have this, and you're another person in another part of the world has a clock, and it's also ticking at the same rate. And then Einstein showed with special relativity, if you're traveling at a certain velocity v, the clock tick rate is slower. So how do we describe that in this theory of spheres called pi space? Now, time is very, very confusing because of the way that it's been taught. So I'm going to explain how it works in pi space, and it's fairly simple, but you have to really understand the concepts in order to really move forward. The first one is there is this concept of a sort of universal time where time moves at a certain rate, and we dispel that notion with special relativity. So what is time for us then? So it's actually fairly straightforward. The atoms in your body, or in any room, they all have a clock tick. So time, the idea of pi space is that the time component of an atom is built into it, right? Each atom has a clock tick. It processes events at a certain rate. So events come into the atom and they get processed, and then there's a reaction to that event. Okay. Now, if you have a smaller, if you're sitting in a room and an object moves by you in that room, it's the atoms in the moving object are smaller based on the theory I've explained already, and the clock tick is slower. It's really that simple. The clock tick is slower. So here's a diagram explaining how to describe that idea. So if you have a smaller pi shell or a smaller atom due to movement, relative movement, your clock tick is slower. Okay, so now there will come a point where you have no. You could say, what happens when the atom has no size? Well, then what kicks in is probability theory, where it's not about the addition of time, it's about the addition of the probabilities, and then you're into the world of quantum electrodynamics, right? But so this idea of time is actually an atom processing events and reacting to those events, such as a clock on a wall, getting a force applied to it, and the atoms have a certain size, and they process that force at a certain rate. So the way Einstein formalized that idea in special relativity was with this formula. You basically have time. It's proportional, inversely proportional to the diameter of of a of a of an atom, and basically what you see is that time gets slower in a smaller atom. So you can imagine as you fall into a collapsar or a gravity well, you're getting smaller according to this theory, and your clock ticks slow. So an outside observer notices you're slowing down. You're inside the gravity well. All your atoms are the same size. Assuming that the gravity field initially isn't too strong, let's say on Earth, where you're on, or even on a plane, you don't notice on the plane that things are that little bit slower because the amount of change is tiny. You need to be having a very high velocity for this effect to kick in, but it does happen even on even on a jetliner. It does happen. Everybody on the jetliner will be that little bit smaller in terms of their atoms, and then this is how to mathematically represent that idea. So it's the atoms that own the clock tick. Think of an atom as owning time. It has its own clock tick. That's the idea. If you look at quantum electrodynamics, the Feynman lectures, one of the interesting things is when he drew diagrams of these probabilities, he had a sort of like a circle with a clock hand moving around at a certain rate, spinning around. So if you could imagine an atom having a similar clock hand moving around, maybe in a clockwise manner, indicating forward time, the smaller atom, the clock hand moves around more slowly. Here we go. So we have the person in the rocket, traveling at a particular velocity, which is 0.6 at the speed of light. On Earth, you get 50 years of time. On the Earth, you get 50 years of time, and on the spaceship, you get 30. We move on to what's called the unit of length, and the same idea here. When the atom gets smaller, the pi shell gets smaller. So it's the diameter shortens, therefore it gets smaller. The sum of the diameters represents the unit length. So each atom is unit length. So each one gets smaller. The unit length gets smaller. So again, it's the unit length. X is equal to x0 times the transformation. So you can see that the length shortens. So you're on the rocket ship. You're traveling at a particularly high relativistic speed. Your clock tick is shorter, but your unit length is shorter. You don't see that because all the atoms in your body are that bit smaller. Everything is sort of scaled down, including the clock tick. Speed is distance over time. The distance it shortens, and the clock tick it goes slower or relatively lengthens relative to the other observer, and they cancel each other out. So the observer on the ship doesn't notice this, and it's a beautiful design. It's a beautiful design. And then when you try, everybody in any frame of reference has a maximum speed of light c. In other words, your atom can be compressed up to speed of light c no matter what size atom you are. Okay? And this is formalizing that idea that speed is distance over time. And then we have this other formula which just shows the adjustment to distance and time, and they cancel each other out. So in all frames of reference, everything appears consistent. It's a beautiful design. The next slightly thornier issue, I'll finish on this now, is mass. Mass is inside the atom. It's essentially separate from the actual pi shell. The mass of an atom isn't in the area of the sphere. It's inside it. So, there is this idea that mass becomes infinite when the atom gets smaller. The It's not that the according in this theory of spheres or pi shells, it's not that the mass becomes infinite or that the object becomes heavier. It's just that it becomes harder to push. In other words, when you apply a force on a smaller atom, you have to apply larger energy to it, unit energy, because there's less area to work on. So it's not that it becomes heavier, it's just that it becomes smaller. This could be a bone of contention for some people who may disagree with this, but this is what the theory states. I have a relativistic energy formula which shows that idea. According to the Einstein formula, it goes to mass goes to infinity. I have a formula in the pi space theory which shows that we don't produce infinity. The work done on the object can be infinite, but the energy of the object itself it doesn't go to infinity. But you can apply infinite energy to something that's so small and not affect it, such as in a cyclotron or an accelerator. So I could understand why people who work in this area might say it does become heavier because we apply the energy and then we get no effect, so it must be getting heavier. And I say, well, it's because the particle gets smaller, and therefore the force that you're applying to it has less effect on it. So it's you could argue it both ways, but that's essentially how it is described in the pi space theory. It doesn't invalidate the theory; it's just an interpretation of what's happening. So you can see the atom gets smaller, and therefore the official formula in special relativity is the division here. So it gets relatively heavier to the point where it gets infinite. So the way I describe that infinite point is here is that it becomes just tiny. It goes and heads towards the wave version of itself. And the interesting thing in the pi space theory, I'll finish on this note, is um, there all all that atoms are really doing is regulating probability. It's a probability regulation field, and when an atom kind of collapses into this lower state, the probability of certain things happening are altered. You go to more towards a probability based theory, which is what quantum electrodynamics do. So in other words, when you're dealing with a subatomic particle, there is a wave behavior and a particle behavior. There's that famous experiment where you put the subatomic particles through these filters, and people get very confused because they see both a wave behavior and a particle behavior. And the reason for that, according to this theory, is when an atom is subatomic and is so small that the diameter is so small relative to the mass, the wave behavior begins to also dominate. It works in both it works with both behaviors, where you get the wave behavior and you get the particle behavior. In a large pi shell or atom such as our own, you get particle behavior. So that's how you explain in pi space the wave and the particle behavior. It's to do with the amount of mass relative to the surface area. So that's that described in pi space.